Does Santa Claus exist? This question has haunted us since the dawn of time. Many people have tried to answer this question in the negative by using mathematical arguments, but they are all wrong. In this video, I am going to settle this question once and for all by proving, using mathematics, that Santa Claus really does exist. The start of the proof will be fairly logical. We are starting with the proposition, Santa Claus exists. This is a statement that is either true or false. At the moment, we don't know whether it is true or false. Let's look at another proposition that should be easier. What about the statement, 2 is not equal to 1? Is this true or false? Well, we know that this is true. It might not seem like we've accomplished much, but let's now combine these two statements. Because we know that 2 does not equal 1, we know that at least one of these two statements is true. Make sure you understand what we have done here. We know that at least one of these two statements is true because we know that the second one is true. When you realize what we are saying, this is really quite trivial. However, this step is key to the whole proof. Now we're going to switch gears and do some algebra. Don't worry, we'll get back to Santa soon. Let's say we have two arbitrary numbers x and y such that x equals y. We are now going to do what seems like pointless algebra to this equation. First, we will multiply both sides by x. Then we will subtract by y squared on both sides. The left-hand side is the difference of two squares, so we can factor it. We can also factor out y on the right-hand side. It might look like a mess at this point, but we are now going to start simplifying. Notice that each side has a factor of the form x minus y. Thus, we can cancel them. We started off by saying that x is equal to y, so we can replace every y here with x. Then we can add and cancel the x's. Thus, we see that 2 equals 1. We can now use this going back to Santa Claus. Now that we know that 2 equals 1, we see that it is not the case that 2 does not equal 1. However, we already saw earlier that at least one of these two statements is true. Because we now know that the second one is false, the first one must be true. Thus, Santa Claus exists. Okay, I can tell you're not convinced. However, if you ask any logician, they will tell you that all of these steps shown on the screen are perfectly valid. All of these steps relied on one pivotal thing, the proof that 2 equals 1. I can understand if you are skeptical of this one fact. Thus, I am going to provide you with several proofs that 2 equals 1. Hopefully, by the end of this video, you will see that Santa Claus must exist. So far, we have seen the proof with algebra. Now, I will prove that 2 equals 1 using derivatives. Observe the following pattern. 1 squared is 1. 2 squared is 2 plus 2. 3 squared is 3 plus 3 plus 3. 4 squared is 4 plus 4 plus 4 plus 4. In general, x squared is x plus x and so on, x times. Now, I'm going to take this last equation and find the derivative of each side. On the left side, we can just use the power rule. On the right side, we can use the sum rule. Now, we know that 1 plus 1 plus 1 and so on x times is just x. We can now cancel the x's. Thus, we see that 2 equals 1. This completes the proof with derivatives. We will now look at the proof with integrals. Consider this integral. To solve it, we will try using integration by parts. Let u equal 1 over the natural logarithm of x, so dv is 1 over x dx. Then v is the natural logarithm of x. du is a bit trickier, but it can be evaluated using the chain rule. We can now use the formula for integration by parts. After a bit of simplification, we see that we actually have the same integral on both sides. Thus, we can cancel the integral. Now we just need to add 1 to both sides, and we see that 2 equals 1. This completes the proof with integrals. We will now look at the proof with limits. Consider this right triangle where each of these two side lengths is 1. Using the Pythagorean theorem, we can determine that the length of the remaining side is the square root of 2. However, I will now show you a new way to calculate the length of this side. Let's finish drawing the square surrounding this triangle. We know that each side of this square has a length of 1, so the total length of these new segments is 2. Now let's bring part of these segments towards the triangle like this. Once we have done this step, you can see that the total length of these segments is still 2. We can repeat this step, and the total length is still 2. No matter how many times we repeat this process, the total length of the segments is always 2. In the limit, these segments become the diagonal line on the triangle. Thus, we see that the length of the diagonal of the triangle is 2. Now, you may think that this step is invalid, but notice that this is just like an integral. If we couldn't do this, we shouldn't be able to integrate either. We saw earlier that this length is the square root of 2, so we now have 2 equals the square root of 2. If we take this equation, square both sides, then divide by 2, we once again see that 2 equals 1. This completes the proof with limits. We will now look at the proof with rational numbers. Most of us learned years ago how to add two rational numbers. You multiply the top and bottom of each fraction by the denominator of the other fraction, and then you can just add the numerators. We can generalize this process for any two rational numbers by using this formula. While we learned this just as a technique for adding rational numbers, it turns out that mathematicians usually use this formula as the definition of addition for rational numbers. The addition and multiplication on the right-hand side of the equation is integer addition and multiplication, so there is no circular logic here. We can define the other usual operations on rational numbers with formulas like this as well. There's nothing stopping us from defining a new operation on rational numbers. For example, let's look at the definition of addition again. Let's make a new operation, which we'll call O+, that is like addition, but where we swap the b and the d in the numerator. To try to get a feel for this new operation, let's see what 1/2 O plus 1/2 is. Using our formula, after a bit of simplification, we see that 1/2 O plus 1/2 is equal to 1. Let's try another one. What's 1/2 O plus 2/4? Like before, we use our formula and simplify. Thus, we see that 1/2 O plus 2/4 is 5/4. But since we know that 2/4 equals 1/2, we know that 1/2 O plus 2/4 is equal to 1/2 O plus 1/2. We already calculated both of these values on the left, so we can use these values in the equation on the right. Now all we need to do is multiply by 4 and subtract 3, and we see, once again, that 2 equals 1. This completes the proof with rational numbers. We have now seen 5 proofs that 2 equals 1. By this point, you should be convinced. Santa Claus exists. Alright, let's actually get serious about this now. Something is obviously wrong with the proof, but what is it that's wrong? Many people think it's the fact that this argument could be used to prove something else, such as saying that Santa Claus does not exist. And it is true that the same argument does work to show that this is true. I could use it to prove any statement that I wished. However, this is not the problem with the proof. This part of the proof is a demonstration of the principle of explosion, which states that if you assume two contradictory statements, you can prove anything. This is a basic logical principle, and it shows just how important the law of non-contradiction is. In my proof, I provided two contradictory statements by saying that 2 doesn't equal 1, and then proving that 2 does equal 1. Thus, I could prove anything. Because I could prove anything, I proved that Santa Claus exists. Since this part of the proof was correct, the only part of the proof that could be wrong is the proof that 2 equals 1. But we had 5 proofs that 2 equals 1. Could they all be wrong? Well, it turns out that every single one of these proofs has an error in it somewhere. Really, the point of this video is not to prove that Santa Claus exists. The real point of this video is to be a lesson in rigor. Many times, when you are trying to prove something, you might make a mistake and accidentally prove something that is false, such as proving that 2 equals 1. When this happens, you need to go back through your proof and figure out where you went wrong. Now, you might think that we wouldn't need to inspect the proof because we have reached an obviously ridiculous conclusion, so of course the proof is wrong somewhere. However, there are times where you aren't sure if the conclusion is correct or not, and if you made a mistake in the proof, you might have accidentally proved something that isn't true. Here's a historical example. Take any polyhedron, like this cube. We can see that this polyhedron has 8 vertices, 12 edges, and 6 faces. If you take the number of vertices, subtract the number of edges, and add the number of faces, we see that the result is 2. Checking several other polyhedra, it seems that the result of this calculation is 2 for all of them. Several well-known mathematicians even gave proofs that this is true for any polyhedron, and some of those proofs were widely accepted. However, consider these polyhedra. On the left, there are 16 vertices, 32 edges, and 16 faces. On the right, there are 16 vertices, 24 edges, and 11 faces. In these cases, if we take the number of vertices, subtract the number of edges, and add the number of faces, we see that the result is actually 0 on the left and 3 on the right, contradicting what was thought to be true. Thus, we see that there had to have been a flaw in the proofs that had been made. If the people who made these proofs had found the flaws when they wrote them, people wouldn't have believed a false theorem. This is why mathematicians care so much about rigor. If we aren't rigorous, we might accidentally start believing things that are not true. So we see that the ability to find errors in proofs is a useful skill to have. Thus, before we move on to finding the error in each of the proofs I gave, see if you can find the errors yourself. You may not be able to find all of the errors, but you should still try to figure out as much as you can. Now, let's work through each proof together to see what went wrong. We'll start with the proof with algebra. Here is the entire proof written out. Let's number the equations to make it easier to talk about them. Something seems obviously wrong in equation 4. Both sides of this equation are exactly the same, but there's this extra x term on the left. It seems that something had to go wrong in the factoring. However, the formulas we used for factoring are always valid. It couldn't have been the factoring. Every step seems to be a valid algebraic step, so where could the problem be? Let's try to make things less abstract. Where does this proof fail if x and y are equal to 1? So with this example, we see that it breaks on equation 5, not equation 4. Wait a minute, let's go back a bit to this part of the calculation. In going from equation 4 to equation 5, we canceled the 0. That means that we divided by 0. So this was the problem when x and y equal 1. Let's look back at the general case. In the general case, here is the step that caused us trouble when x and y were equal to 1. Remember that we started this whole process by saying that x is equal to y. Thus, x minus y is 0 no matter what values x and y take. This means that in this step, when we canceled x minus y, we were dividing by 0. Thus, the proof with algebra is invalid. Let's now try to find the problem with the proof with derivatives. Let's look at when we differentiated this equation. I think we can all agree that there's no issue with differentiating the left-hand side. That leaves the right-hand side. We differentiated by using the sum rule. We can use the sum rule, right? Let's think about this situation in general. Let's say we are adding x to itself any number of times. To differentiate, we have been using the sum rule. After using the sum rule, we recognize that 1 plus 1 plus 1 and so on n times is just n. If you want to be really pedantic about it, adding a number to itself a certain number of times is the basic definition of multiplication. So this expression here is actually n times 1, which is just n. Hey, if we've actually been multiplying this whole time, can we really use the sum rule? Let's go back to the beginning. When we are adding x to itself n times, we are actually multiplying x by n. At this point, we can pull the n out, then differentiate. Wait, we got the same answer as when we used the sum rule. So is there not an issue here? The only difference between this situation and the original one is that here, we added x to itself a particular number of times, whereas originally, we were adding x to itself x times. Let's do the same process on both of these expressions. Maybe we'll find the problem that way. We first rewrite the sum as a product. So far, so good. Now we can pull the constant out and... Hey, wait a minute. On the right, we can't pull out x. It's not a constant. So, here we see a problem with this way of differentiating this expression. But why does that make the sum rule invalid here? Notice that when we changed this to multiplying, it was this x here that was causing us trouble. We assumed that it was constant when it actually isn't. Hey, isn't that the same thing that we did here when using the sum rule? When we applied the sum rule, we differentiated with respect to all of these x's, but we didn't differentiate with respect to this x. So here's finally our problem. When we say to differentiate with respect to x, we need to deal with every single x, and we miss the x that told us how many x's to add. Thus, the proof with derivatives is invalid. Let's now move on to the proof with integrals. We started with this integral. We then used integration by parts to get to this equation. To keep you from needlessly poring over my calculations, I will tell you that my use of integration by parts and all of my algebraic manipulations up to this point were correct. This equation is true. At this point, all we had to do was cancel the integrals, and we saw that 0 equals 1. So then what's the problem? The answer here is that we made a mistake that is very common among beginning calculus students, but it was disguised. Think about what this integral will actually look like. It will be some function plus a constant of integration. We can then substitute this result in the equation below. But wait! Because these were two different integrals, we actually need two constants of integration, not one. At this point, we can cancel f of x on each side. Unlike before, we don't have a contradiction. There are plenty of values that c1 and c2 can take to make this equation true. In the end, our problem was forgetting about the constant of integration. This one might still be tripping you up, because we are often taught in school to do a similar manipulation. Consider this integral. After doing integration by parts twice, we end up with this equation. At this point, textbooks tell you to move the integral on the right to the other side, at which point the integral is pretty much solved. The difference between these two cases is that in the first case, we were subtracting two integrals, while in the second case, we were adding two integrals. Let's inspect these two cases in detail to see where they differ. Like before, we know that this integral is some other function plus c, so we can now write these integrals in terms of this function. However, like before, we need to use two different constants of integration for the two different integrals. Simplifying a bit, we see that in the equation on the top, we are left with some constants. However, in the end, those constants together will be some other constant. Before doing the same thing in the equation on the bottom, we can factor out a 2. At this point, this term here is just some constant. We see now that this part here is the same as what we said our integral is up here, so we can substitute the integral back into the equation. So we see that adding integrals in this way is valid, but subtracting integrals in this way produces a constant, not 0, so it is not valid. In the end, we have shown that the proof with integrals is invalid. Let's now move on to the proof with limits. In doing this proof, we found a sequence of paths that converged to the diagonal side of the triangle. We then asserted that the length of the limit is equal to the limit of the lengths. But is this statement really true? It seems like it isn't because it gives the wrong number here. But then what about integrals? Why can we find the area under a graph by finding the limit of a sequence of areas? Notice that when integrating, we are finding the area by saying that the area of the limit is equal to the limit of the areas. These are actually two very different statements. So comparing finding the length of the side of the triangle with finding an integral was actually a false equivalence. These statements of the form, the blank of the limit is equal to the limit of the blanks, are not true in general, and if you find a situation where it is true, it is often an important theorem. In the end, we see that the proof with limits is invalid. Finally, let's move on to the proof with rational numbers. What we did was define a new operation on the rational numbers, which we called O+. We calculated 1/2 O plus 1/2 and 1/2 O plus 2/4, which should be equal because 1/2 is equal to 2/4. However, when we actually did the calculations, we got two different values. So what's going on here? The problem here is related to the way we define rational numbers. We usually think of rational numbers as a pair of integers, one representing the numerator and the other representing the denominator. However, in the end, a rational number is just a pair of integers. Now with rational numbers, we say that 1/2 is equal to 2/4. But when thinking about it in terms of pairs of integers, these pairs aren't equal at all. So we see that rational numbers aren't just pairs of integers. Rational numbers are pairs of integers with a new definition of equality, where two rational numbers are equal if the two fractions are equal after reducing them to lowest terms. A simpler but equivalent condition is if AD is equal to BC. It turns out that once you have defined equality, defining operations becomes much more difficult than just giving an equation. You also have to prove that this new operation is consistent with the equality that we have defined. Mathematicians usually call this condition being well-defined. In this case, for our operation to be well-defined means that for all rational numbers a, b, c, and d, if a is equal to b and c is equal to d, then AO plus c is equal to BO plus d. It turns out that all of the usual operations on rational numbers satisfy this condition. However, it is false for O+, so O+ is not a valid operation on the rational numbers. Because O+ is not a valid operation on the rational numbers, the entire proof breaks down. If you want to learn more about this idea of defining equality, look into equivalence classes. Anyway, because our operation is not actually a valid operation on the rational numbers, we see that the proof with rational numbers is invalid. Because none of these proofs were valid, we see that the proof that Santa Claus exists is not correct. Wait a minute. I said that this video would have a mathematical proof of the existence of Santa Claus, but it turns out that there isn't? What kind of clickbait video is this? Well, buckle up, because now we will be moving on to the true mathematical proof of the existence of Santa Claus. Think about the number 3. Does it exist? While we can think of things that exist in the physical world that are examples of 3 things, the idea of 3 itself doesn't seem to appear in the physical world anywhere. However, the idea of 3 itself seems like it does exist, at least in some abstract sense. So 3 does exist, even if its existence is not physical. Similarly, even though Santa Claus might not exist in the real world, he still exists in an abstract sense, just like the number 3. Because mathematical objects exist, we see that Santa Claus does in fact exist. And that is the true mathematical proof of the existence of Santa Claus.